Hello everyone and welcome to FU Money Devlog number 1. So in case you don't know, FU Money is a little indie game that I'm currently developing, and it features coding and finances that I'm currently working on. There is a demo available on itch.io and a Kickstarter running at the moment, so you can check out the link in the description. Anyway, in this video we'll see how to generate customizable market-like chart like these ones here, because I consider it to be the most interesting part of the code. So you might be interested if you want to build a similar feature for your video game, or just if you're curious. Okay, so let's start from the beginning. When I started to work on that, I had two options. Option one was to take something that already exists, like GBM. And as you can see, GBM looks pretty good, but it will be hard to implement and control inside the game. And I needed something that I fully understand and control. So that's why I decided to do my own top price simulation. So my solution is split into two temporal scale. There is the micro scale, which is short term and captures noises. And there is the macro scale, which capture longer trails of the market. What I like about my solution is that it's highly customizable. As you saw earlier, you can get pretty much every market shape that you want. It's also easy to reuse for your own games. And overall, it's not that complicated to understand. And a quick note, this Jupyter notebook is available in the description. So if you want to play with it, go ahead. So this first cell here is just about importing a library that I use and also defining some utilities function like the ones to plot charts. So I will just run it and move on. If you're curious, you can look about it, but it's not the point of this video. And that brings us to the macro scale part. But before looking at the code, there are some math to know about, which is the normal distribution. So in case you don't know, a normal distribution is just a bell curve. And in this video, we'll use it as a random number function, so an RNG function. And how does that work? Well, for each number on the x-axis here, the y-axis give us the probability of that number to appear. So you've probably used RNG function before, and it usually gives you a number between 0 and 1. And this generator that you usually use follow a uniform distribution, which means that there is as much probability to get a value around 0, let's say, if a equals 0, than a value around 1 in if b equal 1. And as you can see, it's not the case with the normal distribution. For example, on the blue curve here, you got more probability to have a value around 0 than a value around 1, unlike the uniform distribution. And so this normal distribution takes two parameters. One is the mean, which is the top of the curve. For example, on the green one here, it's -2. And it also takes the standard deviation, which gives you the shape of the curve. A standard deviation around 0 will give you a very pointy curve like the one here, while a larger number will give you a more flattened curve like the orange one here. That's it for the parameter, and as an output, you will get a random number following this distribution. And to give you an idea on how the output number might look like, you got 68% chance, so around 2/3 of the time, that the output value will be between the mean plus minus the standard deviation. So if you look at the red curve here, the standard deviation is 1, so around 2/3 of the value that it will output will be between -1 and 1. And you also get a 95% chance of the output value being between the mean plus or minus 2 times the standard deviation. And you're pretty sure to have a value between the mean plus minus 3 times the standard deviation. Okay, we're done with math for now. Let's see the code. Okay, so with that in mind, let's build our first curve. We'll do so by taking an initial value and then in a loop add random numbers to it and print the value over time. So for this script, we got 4 parameters. The base market value, which is the initial value, the mean and the standard deviation of the normal distribution, and the number of iterations. So this is the main code. First, we initialize the value with the base value, and we initialize a history array with the base value inside. And then we iterate, and in the loop, we get the random number. So as you can see, this is not the random number function of Python, the one from NumPy, and we give it the mean and standard deviation that we set in the parameter. Then we add this random number into the market value and we happen it in the history. And then it's just plotting. Okay, let's run this. And as you can see, we got a pretty decent looking curve that is going up and have some noises. And if we change the standard deviation to a lower value, let's say 5, and run it again, you can see that the noise almost completely disappear and it's almost just a straight line. So the standard deviation controls the fuzziness and noise of the curve, which is the volatility of the market. Okay, let's put that back to 50 and now we can try to put the mean at a negative value and run it again. And as you might expect, the curve is now going down. So the mean controls the steepness and the direction of the curve, which is equal to the average gain of the market. And we can also put it to 0, for example, and it will just generate some random noises around the base value. Okay, let's put that back to normal. And you can see that we can compute the expected market value at the end of iteration, which is the base value plus the mean times the number of iterations. So it allows you to get a bit more perspective on what number to expect, and it's useful when you build a game. And you might notice that the curve looks good, but there's something missing, which brings us to step 2. And the problem is, where is the stonks? And as you can see, it's a linear line, it's a straight line. So there is no compound interest effect that we have on the market. And the solution for that is pretty simple because we can use the product instead of the sum. So as you can see, it's pretty much like the previous script, except for this line here, where instead of doing plot the sample, we will multiply by 1, which corresponds to the current market value, plus the sample divided by 100 because the mean and the standard deviation are in percent. Okay, let's run it. And you can clearly see the stones here, the exponential curve, where it's very low at the beginning and it goes up very fast. And if we put a negative value, we got an hyperbola type of curve, which means that it's going down rapidly and then it flattens because we don't have much left to lose. And we can also compute the expected market value at the end of iteration. It's a bit more complicated. It's the base market value time the mean to the power of iteration. So in that case, it will be 4. So that's it for the micro scale. As you might notice, it will be cool if we had something, a system on top of that modify the mean and standard deviation over time. So we'll get an overall curve that have trends of ups and downs with different steepness and noises. And that brings us to the macro scale part. So as for the micro scale, there are some math stuff to know about, which is the Markov chain. Don't worry, it's not that complicated. A Markov chain is just a state with probability of transitioning from a state to another. In this example, if you're in state A at the next iteration, you have 60% chance of staying in state A and 40% chance of going into state E. And if you're in E, the next iteration, you got 30% chance of staying in E and 70% chance of going back to A. And we can represent this graph in what we call a transition matrix, where each row tells you the probability to go from the state of the row to the state of the column. So in this example, going from state E to state A is 70% as we see here. Okay, with that, let's code some market state. So for this script, we got 3 different parameters. We have the transition matrix. I build some market state here, which are from top to bottom, from best to worst. Bubble state, boom, bull, stable, bear, decline, and collapse. And you can see that for each row, the sum is equal to 100. So it's not mandatory, but it's just easier to read. You can see with the diagonal here that all the states have a high chance to going back to their own state. For example, the stable state have 95% chance of staying in the stable state, while it have only 2% chance of going into a bull state. So the general idea for this matrix is that the further you go from the stable state, the more unstable the states become, as you can see with these numbers. And also there is a higher percent chance of going to a total opposite state, like the bubble have 0.5% chance of going into a collapse state, while this stable state doesn't go very far from itself. Anyway, that's just an example. You can actually delete or add other state and tweak the number the way you want. Anyway, moving on, we got the second parameter, which is the base state. In that case, it's the stable state. So it's in order from top to bottom. So bubble is 0, boom is 1, and so on. So we got stable state here. And finally, the number of iterations that will run the simulation. Okay, let's see the main code here. First, we initialize the current state with the base state that we set in the parameters. And we do a state history, a bit like what we saw earlier, where we put the current state. And then we get all the state from the transition matrix. So state will have all these values here. Then we take all the weights from the transition matrix. So the weighted transition matrix will hold all these values here. And then we will normalize the transition matrix so that the sum of every row is equal to 1. I also printed this normalized version, so it's easier to read than this one. Then we got the get next state function, which will tell us the next state of the iteration. So it has two parameters, the current state and the transition matrix, and it outputs the new state. And as you can see, the transition probability here will take the row of the current state. So for example, if the state here is stable, so 3, it will take this row here. And then with this row, it will give a number based on the probability. Okay, we arrive at the simulation where we loop over iteration. So this is pretty basic. We get the next state by calling this get next state that we saw. Then we say that the current state is equal to the next state. And then in the state history, we happen the current state. And then we're just plotting the simulation and putting some insight that we'll see later. Okay, let's run this. So as expected, in the output, we got the normalized version of the matrix and we got the market state simulation. And as you can see, it starts with the stable state because this is what we put in parameters. And you can see that then it transitions at around iteration 15 or something. It goes into a ball state for a short period of time. And then it goes to a decline state and so on and so forth. And you can see that most states stay for at least a couple of iterations. And that is because in the transition matrix here, we got big value here. If we lower this value, for example, you can see that it will get quite messy. Run it again. And you can see that it's quite messy and almost unreadable because states are not stable. And this is where the first insights come into place. Let's just put back the normal matrix first and run it again. So as you can see for this graph, it showed the state stability. So to go deeper into this graph, for each state, you got the probability that it will stay for a number of iterations. So in this example, the stable state in red have 60% chance of staying for 10 iterations or less. And as you can see, the more unstable states are, the less chance it have to stay for a long time. We can put more instability in the transition matrix and see how it looks. If I do this and run it again, you can see that in this graph, all states are much more stable. Anyway, let's put that back to normal and run it again. And the last insight that I wanted to talk about is the steady state, which tells you on average how much time a state will be present. And you can see that the stable state, for example, will stay around 45% of the time in total. So if we change the matrix and makes every state going to stable, for example, if I put like this 100 every time, you can see that the stable state will be present 91% of the time. And if we look at the simulation, it looks true. So you can see that the state stability and the steady state are two insights that complement each other. One tells you how likely a state will stay, and the other one will tell its overall presence. And it's very useful to get a grasp on what happened when you put these numbers here. Okay, let's move on to the last part, which is to put the micro and macro parts together. As stated earlier, the state of the macroscale will change the parameter of the microscale. So for the parameters part of this script, we got a mix between the micro and macro scale. The only new parameter is this one, which gives you for each state the mean and standard deviation of the RNG function. For example, in the stable state, it will slightly go up, while in the bubble state, it have a much steeper curve. And in a collapse state, it will rapidly go down. In the parameter, you can also switch compound interest effect on and off. So it will either take the product or the sum. As for the core code, it's really a mixed between what we saw earlier. The only new thing here is the parameter of the normal distribution here, which come from this parameter, and we take the current state of the simulation, and we take these two parameters here. As you can see, the mean is here and the standard deviation is here. Okay, let's run this and see what happened. And here we go. We got a nice looking curve here. I don't know what you think, but I think it looks pretty convincing, and you can clearly see how every state influences the shape of the curve. For example, here you got a bubble and you can clearly see this steep curve going up here. And then we got a small decline and collapse here, for example. And it's really convincing, in my opinion. We can run a couple of more, and you can see that the shape of the curve is really different every time. Anyway, feel free to check it by yourself and play with it if you want. Anyway, for the last part, I wanted to have some insights about the system as a whole. So I tried to do it myself, but it was quite difficult. So I asked ChatGPT, and this is what it gives me. I won't explain this code because honestly, I don't understand some part, but let's just run it and see what it gave us. So it gave us a plot box of the expected market value after the number of iteration that we give it. And in this example, the market value is set to 200 here. And you can see that after 1,000 iteration, you have 50% chance of being between, let's say, 250-ish until 270-ish. The next plot box is the same but expressed as a percent. So you got 50% chance of having around 25 to 35 increase of the market. And the last graph is basically the plot box, but just over time, over the iteration here. And you can see that at the end, we find again the two value 250 as a low quarter one here and 270 as a quarter three. And lastly, the same but expressed as a percentage. And to give you an idea, I asked ChatGPT to explain how it did it, and this is its response. You can pause if you want to read about it, but my brain started to hurt at step 4 here. I couldn't understand anymore. And basically it was able to embed the system as a normal distribution, which is pretty crazy. Anyway, that's pretty much it. If you want to adapt it for your game, I got a few ideas for you. For example, if you want to have tight control over what the player gains and losses, I recommend you to not implement the compound interest aspect because it can get out of hand pretty quickly. You can also run macro and micro iteration at a different pace if it's more manageable for your game. If you want to go further with the market-based system, you can try to embed previous and current state into a single state. So for example, let's say you are in a collapse state, but the previous state was a bubble state, so you want a rebound. Well, you can do that by creating a special state which we can call a collapse after bubble. And this state is only accessible from the bubble state, and it has custom transition. But keep in mind that the more states you put, the more value you will put in your transition matrix, and it can get out of hand. And lastly, every variable and every parameter that we saw can be computed dynamically. So for example, if you're making a management game and your player play very badly, you can change the transition to increase the chance of a collapse, or the reverse if the player is playing well. Anyway, you get it. Feel free to adapt it to your own situation. And that's pretty much it for this video. Overall, I really enjoy doing this. There is a little bit of math, a little bit of creativity, and I really enjoy doing this. And if you like the video, don't forget to like, subscribe, because I might do other devlog about this project or other ones. And quick reminder, you can try the demo of my game on itch.io. It is my very first game, and I'm more of a backend guy, so the UI and the graphics are pretty bad, to be honest. And unfortunately, everything that we saw here is very limited in the demo. As you can see, I'm still working on it, even if I have the base core of the code. And if you like it, you can check my Kickstarter page. Every donation will be much appreciated. Anyway, thanks for watching, and see you later.